my screen, and Martina, you can share your screen.
Yes, I will try to do so. Hopefully, I still have everything open. Yes. Share this, present this. I hope you have the right. No, I think you're seeing the wrong screen now, right?
I see the presentation, but not in the presenter's mode.
Yes, exactly. That's what I feared. Let me just check how I can switch that. What was the trick again? I'm sorry. That usually works right away. Um,
I actually don't know. Maybe it's this button. No, it's
God. Okay.
maybe display settings on top.
Yes. To swap
Might be
present.
that.
Yes. Perfect.
Yeah,
Thank you.
exactly.
All right, sorry, I had a long day already. I mean, it's only 5 p.m., but still after a whole work day. I would also have an excuse if it was early in the morning, so don't worry about that. So thanks so much for having me. Sorry for the technical difficulties. I will just start by basically giving an introduction what our lab is generally doing, and we'll then go a little bit more into detail on one of our latest papers by a postdoc of our group, then to also give Oskari some room to present what he has done in his PhD so far. I'm very excited about this presentation, with this invitation as well. And I already saw some familiar names, so thanks everyone for coming in, and I hope you will enjoy a little bit the talk that's to come. And I will just try to make this smaller so I can actually see my own screen. Perfect. So I will talk about coenzymes as a connection between mineral-based and enzymatic catalysis en route to metabolism, and I hope by the end of this talk you have somewhat of an idea what I mean by that. So, but first of all, I would like to take the opportunity to thank my group that actually, especially now this January, increased in PhD students quite a lot. So usually the group is not that big, but it's now thanks to the European Union. But I'm really excited also for what is yet to come. And what we have already done, but it would not be possible with all the great people that we have here, and also the surrounding that we have here in the beautiful tiny city that is Marburg in the middle of Germany. And just already, before I forget, at the end, we're currently also looking for especially chemistry, a chemistry PhD and a postdoc. So if after all of this you're interested in maybe joining the lab, just shoot me a message and we can get together. All right. So what our lab is mostly interested in is how did we get from here, so an abiotic environment of sorts, like for example, an oceanic crust that you can see on the left-hand side here. Maybe I can actually go for already the pointer options. Oh, the pen was wrong. Yes, perfect. So like an oceanic crest, which is a microscopical image of one of them, to something like this. So first single cellular organisms such as archaea and bacteria, methanogens, acetogens. So when it comes to life and we look at life, of course, it's my PhD supervisor always said life is a chemical reaction. So, well, that's in many ways very true, but it needs to be catalyzed by these beautiful structures. So enzymes, they come in many forms and shapes, and without them, life would not be possible. They enhance the reactions that make life, that provide life, and that is on one side very beautiful and very cool, and but on the other side, looking from a prebiotic perspective, from a origin of life perspective, unfortunately, enzymes are also extremely complex. So it's really hard to imagine that they just popped out of nowhere and enabled life. So to make this thought a little bit easier, to also see where would we get if we don't have such complex constructs like enzymes, we can maybe just biochemists hate this, but if you extract the protein of this whole equation, what are we left with? So a lot of enzymes actually employ metals and also minerals in their active centers, and we would also be left with organic cofactors, so simpler organic molecules that also enable the reactions of life. So in order to also approach this question a little bit closer, we can also look into bioinformatics and the phylogenetics to have somewhat of an idea how to actually look for the most conserved functions of life. And I'm not a phylogeneticist, so I think actually Val would be a better presenter in this direction. But what I want to get to is if we look for the most conserved properties of both bacteria and archaea, so single-celled organisms, domains of life that we have today, we would get to a theoretical construct that is called the last universal common ancestor. I am sure that most of you have heard of it, which is the last cell that we can obtain from extant biology, and it, depending on who you ask, but it roughly existed 3.8 billion years ago. And thanks to phylogenetics, we can then make somewhat of an assumption what Luca looked like. That means what did Luca do metabolically, and then also make further deductions, hopefully from that. So when it comes to the physiology of Luca, I usually only present a part of it, namely its carbon metabolism. And when it comes to its carbon metabolism, Luca was most likely a so-called anaerobic autotroph that employed a so-called Wood-Lungler pathway, often also called reductive acetyl-CoA pathway in origin of life research. That means translated it was CO2 fixing, and for that CO2 fixation was highly hydrogen and transition metal dependent. And so you can see, so this is really just the core of the carbon metabolism of this Wood-Lungler pathway. It exists of two branches, just quickly, because I mean, I will not talk about it a lot when it comes to the science later itself, but I think it's a very crucial thing to explain. It exists of two branches, a carbonyl branch and a methyl branch, and in a unifying step between the carbonyl group here and the methyl group here, we will get to acetyl-CoA, which is then also a transitional point to pyruvate. And from there, you can either go to, for example, the reductive citric acid cycle, very important, or Krebs cycle, also very important for metabolism, or also to sugar genesis. So it's really a really crucial part to get from something abiotic such as CO2 and hydrogen to this very important transitional molecule that is acetyl-CoA here in the middle. From this physiology, we can then make deductions on where Luca lived, and maybe also an extension that is at least the hypothesis that we are testing, if we can also make a deduction on the cradle of Luca, meaning where Luca came to be. And we are looking for a geochemically active environment that had sources of CO2, hydrogen, and transition metals, at least when it comes to the carbon metabolism. The rest of metabolism is not a different story, but an additional story that you would also have to look for sources of nitrogen, et cetera, et cetera. For us, the most, or for me, I cannot always speak for my students, they can also have the mind of their own, but what I really like as a concept are so-called serpentinizing systems. So they still exist today. So those are systems where the protons of water are getting reduced by a water rock interaction, where iron 2 is being oxidized to iron 3, and the electrons of iron 2 are being put onto the protons of water to produce continuously hydrogen. So that happens in the oceanic crust nowadays. At the same time, I think I saw Susan Lang also in the audience. So Susan has shown over a decade ago with colleagues that you would also not only find reduced protons, so hydrogen in there, but you would also find reduced, abiotically reduced carbon in these systems flowing out of them. So what also happens in these systems is that actually CO2 and hydrogen most likely react to form organics as well. What is also really interesting about serpentinizing systems is that they come actually in a lot of different shapes. So they can be, for example, this is a rainbow hydrothermal vent field that still exists today, which is a black smoker, so acidic and very hot. You of course have Lost City, which is a so-called white smoker, so rather rather lower temperatures, around 90 degrees, and alkaline conditions. But what I like most about it, it seems to be a very universal process. Just 4 years ago, uh, people around, there was a paper in Science by Steele et al. That showed that this Martian meteorite that you can see here that dropped on Earth in the 1980s actually also showed very clearly that a water rock interaction comparable to what happens in serpentinization also happened on Mars at some point. Millions or billions of years ago. I actually now have to lie because I don't completely know how old it is, but it just really shows how universal the process is. So that does very likely not only happen on Earth, but also happens on other celestial bodies as well. So that is kind of cool. Let's go back a little bit to the enzymatic part of it, so the physiological part. When we look closer into Luca's alleged carbon metabolism, the Wood-Longer pathway, we would nowadays, so by the microbes that still employ it, would find a lot of enzymes involved in this process. Depending on what organism you look at, it would be 9 enzymes or even more. So especially in the methyl branch, you would have a lot of different ones employed. But one that I always show as a good example is our enzymes that are called hydrogenases, because what they can do is basically make the electrons of hydrogen accessible to carbon pathways such as the Wood-Longer pathway. And that is actually not an easy feat. So the thing is, you either have to, when you don't have an enzyme like that, you usually need a really good otherwise catalyst, or you need a lot of high energy, or if you put too much energy in it, something very explosive would happen, like a chain reaction. So it's actually really, really crucial to have an enzyme that is able to harvest the electrons to put it into a metabolic pathway. So what you can also see in the center of this hydrogenase, in this particular hydrogenase, are the transition metals nickel and iron. The nickel-iron hydrogenase is also supposed to be the oldest hydrogenase that was also employed within Luca or parts of it. And we will also cycle back. You will also see in Oscar's talk that nickel and iron are transition metals that always kind of are in our mind, and we really use them a lot to figure out our prebiotic chemistry. So the question is now, what was there before enzymes? So if we take away all the proteins and we look in an active center that has transition metals, we are left with something like mineral surfaces, for example, in an abiotic, prebiotic geochemical environment. And this brings me back to like something that is already like ancient history, which was something I did in my PhD, so very long ago. Where we showed that if we have nickel and iron containing minerals that you would also find in serpentinizing systems, those can also actually catalyze the reaction between CO2 and hydrogen in aqueous conditions to formate methanol, acetate, and pyruvate. And when you now have look onto the right-hand side here, those are also the intermediates and products that we would find in the Wood-Longer pathway. That does not mean that we're like close to metabolism or anything, but it might give us a hint that there is actually a geochemical backbone buried within carbon metabolism or ancient carbon metabolism that the rest of life might have built up around. So far, at least the hypothesis. But of course, if you really start from something as simple as mineral surfaces and you try to think about how you could actually reach enzymes, which are undoubtedly a lot more complex, what can we do to actually bridge this thought? And for us, it's not only for us, but also for other people. Coenzymes have been in the focus of research for quite some time now. They have been discussed already like in the 20th century quite a lot, and then were buried a bit and then resurfaced again. But the question is here, can we maybe use cofactors, coenzymes, or organic helper molecules of enzymes to bridge mineral surfaces to enzymes in some way or another? So that means, in other words, can we use coenzymes to maybe also get side reactions of CO2 fixation? Can we maybe even use them to promote products and furthermore products of the Wood-Lungner pathway or precursors thereof, or can we also use coenzymes to get something like small autocatalytic loops in there? This is all based on a lot of literature by like not only theoretical literature but also already a lot of lab literature that people have tested. I cannot name all the names of people that did amazing work in that, but I think it's a really promising route to look into. So in the end, what we want to use coenzymes for is to reconcile biochemistry with geochemistry. And just to give you a little bit something more at hand, how such a transition could look like. Simply put, is like we start from CO2 and hydrogen. We start with the mineral surfaces that, of course, can catalyze and increase the reaction the velocity, basically. So you have a catalyst, but what we also have to reach over time is like to get something more effective and specific. So that means maybe if we have an interaction between coenzymes and mineral surfaces, we already get something more effective and more specific when it comes to certain reactions. Then whatever it would look like, a protoenzyme that is assembled on or to a mineral surface in one way or another. And then in the end, we would have a coevolution of enzymes and coenzymes together with the transition metals that we also find in enzymes today. So this is a very naive view maybe at how this transition could look like, but it was important to me that the point comes across how we're looking at it, or at least what we want to test, or how far we can actually get with this. So right now, our group is roughly 3 years old, a little bit younger. We are really still focusing on the interaction between coenzymes and minerals. So I already told you I brought one example for how we do this. Also one example that is actually published now, which is about making hydrogen and thus electrons and thus also energy accessible to metabolism. And so we are looking into redox cofactors. So we're looking into flavins such as FAD and FMN, but also the most central redox cofactor, nicotinamide adenine dinucleotide, or for short NAD. And Oscar, we will just in a few minutes talk about the flavins. So I will now focus on what we did with NAD. This was mostly Delfina Pereira's PhD work, and she's now still working on parts of understanding these processes even better as a postdoc in our lab. And what Delfina did during her PhD for basically 3 to 4 years is trying to reduce the oxidized version of this coenzyme NAD+ with the help of mineral powders, metal powders, and hydrogen under a variety of conditions. But in the end, it was most important to see if we actually needed hydrogen as an electron donor or not. So we also had argon as a control for all of our reactions. And then we would have these vials where we put minerals in there with a solution of coenzymes, and then we put these in high pressure reactors that we then pressurize with certain atmospheres and let the reaction run. And what Delfina found in her first paper in 2022 was that when you have iron, nickel, or cobalt powder, you can very specifically reduce NAD+ to 1.4 NADH, which means basically this coenzyme is really just reduced at this part of its nicotinamide ring. And that was somewhat surprising to us because that's also the biologically active form of NADH. So in theory, could also get reduced at any other place theoretically of this nicotinamide ring. But after that was published in 2022, and we actually started together in the lab here in Marburg, we thought about simpler precursors of it, because of course NAD already is quite a complex molecule, depending on who you ask. But if we look at a variety of different coenzymes that you can see here, like FAD or SAM or acetyl-CoA, or here on top you have NAD. They all have a universal molecular tail, AMP, or adenosine derived tail. So our question was if all the actual interesting chemistry is not happening on that tail, but rather on on these functional groups like the nicotinamide ring, do we even need that tail? And can we just look at simpler versions of it? We're also not the first ones to look at it, but we wanted to look at it in combination with mineral catalysis. A lot of literature, or most literature so far, has thought these things to be mostly recognition handles for enzymes, and that's also what we thought at the point at this time. Then Delphina started using nicotinamide mononucleotide, so NMN, and started to reducing it the same way she did it with NAD. And much to our surprise, we actually get different results from it. So she would first get the 1.4 NMNH as she would get for the dinucleotide. But then over time, when you see here from 0 hours to 4 hours, the single reduced 1.4 NMNH would decrease, and you would get a lot of different side products that we still had to assign because we didn't have any clue what they could be. So we already saw that something was crucially different from the dinucleotide when it came to the reaction. So when it comes to the assignment, we got a lot of help from Shulan Shi here at the NMR department at the University of Marburg. And we saw that the precursor of NAD does not get reduced very specifically opposed to NAD. We, again, with the help of Shulan, we were able to assign a lot of the peaks that we would see in the NMR. So we would get a hydrolysis product, we would get overreduction product. So there would definitely be something going on that did not go on with 1.4 NAD. So we would start with this, but then something would happen to the molecule that it would not be as stable as NAD itself. So just to give you an idea of how that looks like specifically, if we do the same reaction with NAD over time, we would only get 1.4 NADH and another version of it, which is not overreduction, but also singularly reduced. It's basically just a rearrangement from 1.4 to 1.6. You would have some degradation to nicotinamide, but on the right-hand side with NMN, it would get reduced all over the place. So can you also here see with the sum of reduced compounds, you would get a lot more side products with NMN over the same amount of time, the same conditions that we would have with NAD. So that was interesting to us to see because we actually just wanted to show that we can also reduce NMN as we do NADH. The question is now, why do we even care that NMN gets over-reduced that much? Because in simple terms, the single reduced 1.4 NMNH is a good electron donor that has also been shown by the Moran group, and they used 1.4 NADH to reduce pyruvate to lactate, for example, and the rest, so hydrolysis products, overreduction products, would be bad electron donors, mostly because if you oxidize NADH back to NAD+, you would get back to an aromatic ring. And here, if you do that with any of the other side products, you would not get that, and thus it's thermodynamically not very liked oxidation process. We also did some cyclic voltammetry to also prove that. So here you can see in blue just a standard of 1.4 NMNH, so we can actually see when it gets oxidized. If you have never seen that before, that basically just means you have an oxidation process on an electrode. So here you can see the first oxidation event, so the oxidation of 1.4 NMNH. And then if we have our reaction products in here, we can see that there is even a later at the higher redox potential. Then we actually have whatever reaction products we have in there, they will be oxidized later at higher redox potentials. So it just means that side products are worse reductants than 1.4 NMNH in this case. So we also tested that to really make sure that NMNH can also be a reductant, as it was already shown by the Moran group that NADH can do that. So we did basically the same what Joseph and Robert Meyer did in their paper. We used NMNH, and we could show that as 1.4 NADH and 1.4 NMNH can reduce pyruvate here under the same conditions, the same magnitude. So there was not a great difference between the two, so they're comparably good hydride donors. But the question is now in a prebiotic, under prebiotic conditions, of course, we would not only have 1.4 NMNH, but also a lot of side products. But first of all, you might have wondered why actually is NAD more specifically reduced, and we thought it might be because what NAD does in aqueous conditions, it actually folds. We also got some help from Valentina Erastova's lab in Edinburgh by Sarah Stewart, a PhD student of hers. They did some molecular dynamic calculations showing that we can actually see the folded conformation in aqueous conditions, and it would also prevail when interacting with a mineral surface. And our idea was that this actually could shield NAD from overreduction or side reactions that we see with NMNH. So that means, in other words, that this universal AMP tail actually could protect the active part of the molecule and thus makes that molecule more versatile, although of course also more complex. That was, again, not what we actually wanted to find, but that's what we found. We also saw that it actually makes a difference, which comes back to our comparison between nickel and iron powder. We actually saw that then the metal that we use or the abundance of the metal has an influence if we have more overreduction or less overreduction. So we saw that actually nickel provokes more overreduction than iron, while iron, for example, promotes more the hydrolysis of NMNH, which is mostly likely because 1.4 NMNH, if it's not over-reduced, will most likely rather hydrolyze. So the overreduction by nickel basically shields it from the hydrolysis that happens otherwise. So either way, environmental conditions that we have, whatever your environment is, would actually steer the selection of, might actually steer the selection of a cofactor in a prebiotic environment. So we also did some direct competition experiments where we had both NAD and NMN in the mixture, and 1.4 NADH was always in a higher concentration after the reaction than the 1.4 NMNH, and that was also independent of the catalyst that we used. So in the end, NAD would always give you more of the single reduced coenzyme and thus also of the better reductant in the end. So what does this mean in a prebiotic scenario, or could mean in a prebiotic scenario? So if you look, if you have something with an AMP tail, in that case, NAD, the idea is even in a prebiotic environment, this AMP tail could protect NAD from overreduction and thus would make it selectively better for any further reaction that comes along the way. So we don't lose less active side products as we do with, for example, NMN. We then can, once we actually get hydrides from the mineral surface onto a coenzyme, we would get electrons independent from a surface where we could then also do further reduction steps that I also showed with pyruvate to lactate, for example, or any other reaction. So to sum up, I'm pretty sure that I'm a little bit over time because it's kind of my MO, so I apologize for that. To sum up, that's kind of how I picture the hypothesis that we're working on, regardless of how much will turn out to be factual or true. We start with geochemical processes in a porous geochemical environment such as the oceanic crust, for example. You would have undirected catalysis of mineral surfaces, then also a production of predecessors of coenzymes. Coenzymes could also help to lead to self-sustaining catalytic networks. There's a lot of cool theoretical work, for example, by Joanna Javier on that. And then from these type of self-sustaining catalytic networks, which we also hope to reach at some point in the next years, at least in simple forms of that in our lab, we would get to polymerization and first protein enzymes. That at least how I picture it. It might also change. But so far, we could show that there could be a geochemical selection of biomolecules such as coenzymes. For us right now, it is possible to connect organic cofactors to mineral-assisted chemistries. What we still want to look into in more detail is if there were any precursor molecules to modern cofactors and how would they behave. And we want to see if we can actually create at least parts of non-enzymatic reaction networks that actually are based on cofactors and the whole system starting from the exorganic reaction, that is CO2 reduction with hydrogen. And with this, again, thank you for the invitation. I also want Oscar to actually have some time to talk about his school flavin reactions. So thank you very much. If you have questions, I'm happy to answer them.